Okay, good afternoon. So that's a great pleasure to be here with you today. I want to first introduce myself, Mostafa from South Dakota State. I want to thank my co-PI, Dr. Webby, on the project and or basically graduate student Sandeep Rimal to help us and finish this project. It's a bit more on the structural side than the material, but I think that's very interesting and challenging project that we came up. We want to load rate an old or damaged bridge, and we are focused on double T's. First, let me thank South Dakota DOT and US DOT and MPC for funding the project, and we had many local folks that help us to finish the project. Why double T? There are more than 700 of those in South Dakota. I know that, or neighboring states, they also use a lot of double T's. And the way that they constructed, they have one double T in the span lengths built, ship it on site, put the next one at the side, and they have a key to pour, and then the entire basically bridge is set. These are very common at the local roads, not at the highway or state level roads, and the owners are really the county. So they don't get that much attention of the state DOT or the federal basically assets that we have. And we have seen that 75% of our bridges are 20 years old and older. They should live 75 years. They are not. We are changing them at 45, 50, mainly because of a lot of damages that they get there, and especially in the longitudinal joints. You see a few common damages that we have, and I showed there here. Okay, the big challenge was how you want to include different types of damage that you have in load rating. Let's focus on only AASHTO LRF1, and this is the equation for it. The load rating equation for AASHTO, this version has three main components. Dead load, we are not touching it, it is what it is. The capacity and live load component. Live load is at denominator, and the capacity is the capacity up top. The question is, if you see a particular damage on double T or any other girder bridge, how you want to translate it in this equation that AASHTO has. Currently, there is no study that will relate specific damage to these components. What they have is a general deck level damage. They say if it's good or satisfactory, use a reduction factor of none. If it's fair, what is fair? Use 0.95. And if it's poor, what is poor of the entire deck? Use 0.85 or reduce your capacity by 15%. Nothing specific to element of the bridge, overall deck. So we wanted to see how we can tweak these numbers and be able to load rate old and damaged bridges. Quickly, what we did, we had to change AASHTO definition of damaged state and make it more specific to double T and girders. Then we reviewed 375 inspection reports. We had a frequency of how many damage we have in our state. And we field tested two bridges, nothing super excited, but we did those that had the longitudinal joint damage. We brought two 45 years old severely damaged girders to a lab and we tested to failure. And we did 1,500 analysis to find a relationship between damage and the capacity. I'll go quick over of these topics one by one. AASHTO has a nice table of how you can damage state every single component of a bridge. The one that was for girder ones is general. For example, damage 4 says that is damage state 4. You go and do your structural analysis. No qualitative and quantitative language there. So we had to change it. And for double T, we ended up with more quantitative language. So if you send two inspectors aside, they will report back to you the same damage state. Here are a few examples. For example, if you're at the cover deterioration of the stem, this is what we define as damage state 4. If you are at the transverse bar, that's what we define as damage state 2. And if you are at the longitudinal of the exposed longitudinal tendons, that's what we define as damage state for example, to there. So we try to be quantitative and define those for flanges and for stems, so everyone knows what damage state we are basically referring to. So we went to Rapid City. We are at the east side of the state. And Rapid is on the west side of the state, almost 400 miles away. We went there, we inspected a few bridges there, and we brought two girders back to our lab, which were severely damaged. I guess by flooding, we were not sure about the source, but I think that was the flood that made these damages. Here are the picture of the girders as we received, extracted. These are 45 years old. You can see stem cover, very bad damage toward the end. At the middle, we had flange cover damage, and also at the end, we had exposed reinforcement. And we also had one 30 feet, and we also had a 50 feet long girder. The reason that we picked two different lengths is we want to see if the shear plays into the game of the capacity and how much damage we relate to the capacity. So severely damaged, 45 years old, we tested them to failure in our lab. And I'm just quickly going to show you one of the tests that we did. I want you to focus on the middle of the bridge where those tendons were exposed. Very bad. 50 feet long. That's a slow motion of the same thing. And I want you to take a look at the reaction of my student behind the scene. Here, a few seconds. There you go. You saw that, how bad the testing was. So we lost a few sensors, totally worsened because we didn't know how it would fail. We knew it will fail, we didn't know how bad it will fail. So it was a control. You can see me there, kind of not even moving. I've seen these things before, but that the student poor one didn't see it before. Okay, I wanted to show you some of the damages that we saw during. So it was a stepwise testing from low to failure. So typical cracks that you see everywhere. And then at some point, what we saw that the top flange, which had a lot of cover exposure, crushed before you rupture the tendon, so it was a brittle failure, not a ductile one. And this graph is the best outcome of that girder testing. I have AASHTO service limited state line for this particular bridge or this particular girder there, and I also have AASHTO strength 1 limited state. This girder does not meet any of the AASHTO requirements. It was there, it was alive. People were walking on it, using it. Truck was passing it every single day. It was not safe. So we used that data, and we wanted to say, if you see this damage, most of the one of the legs of the concrete of the leg is gone. If you see this damage, can you really predict this capacity? So that one was the goal. And we did 40 feet length girder, healthy one, new one before this test. And to give you some perspective, it should have shown 10 inches of displacement while it failed at 5.5. So it was really bad girder. And then we did the testing of the 30 feet girder, same behavior, and it failed by a huge crack at the middle of the girder, and we stopped the test before it collapses like the other one. And we wanted to see again, if you see this damage in a 30 feet long girder, can you predict the capacity of it? And again, this girder did not meet any of the AASHTO requirements. So 2 tests we did, we went to literature, extracted all the other tests that we could find, old or damaged ones. And then the last 2 columns are the one that you should focus, and you see that our prediction of the strength is not really that bad, 12 or 13% offset with respect to the test data. So we were happy about how we calculate the capacity. We had 2 ways, shear estimation and moment curvature for the moment, including damage. I'll talk about that later quick. And then we went to a site, not one site, 10 of those, and picked 2 bridges for field testing. The reason that we picked these 2 bridges were the longitudinal joints, the joints were bad. Those were the worst one that we could find. And we wanted to see if you have a truck here, will all the girders see the distribution factor as they intend to see? We wanted to test that. So here are a few basically images of the girder from underneath. You can see the stains of the joints. So these are really poor joints designed 34 years ago, and really not excellent joints as the longitudinal ones. And we tested these guys on field, and we found two different things. First one, you can use AASHTO as it is for damage state 1 to 3, and say AASHTO is okay in estimating the flexural girder distribution factor. Shear one, the same thing. So our instrumentation showed that. So top one is AASHTO, this chart here, and then all the others are test results. So we didn't really pass AASHTO much. So you can use AASHTO there. For damage state 4, when you completely unzip the two girders, we said 6 feet wall spacing or axial spacing, 4 feet girder width. There is no way that you can take more than 50%. We added 10% to that. And we did some recommendation in that. We also did dynamic testing, and we saw that the AASHTO is good to go. So 1 to 3, damage state 1 to 3, you can use AASHTO. Damage state 4, the bad one, unzipped one, we are saying that you need to follow this language to estimate the demand of a damaged girder, especially if the joint is damaged. So we did some work on the capacity side. We have a good model to proceed. We have done some field work, and we know how the girder distribution will look like. Then we come back to this equation and say, okay, do you want to change the live load when there is a damage? That's what you should do. You should do follow our 2-3 recommendations that we did through the field testing. Do you want to include damage of the girder into your calculation? Currently, AASHTO has phi C, phi S, phi, and Rn. No change there. We're taking out the phi C, and we are playing around it. So if your girder is damaged, the capacity of that is the reduction factor that I will give you in a moment, time whatever you're using now for load rating. No change in AASHTO or LRFT design or a load rating one, except this phi C component going into the C component. Okay, here is just one example. Let's say if you are going to have cover deterioration, damage state 4, something like that, you need to reduce your moment, nothing, your shear 25%. Makes sense. And if you are going to have, let's say, exposed transverse rebar, you're not going to touch your moment still remains same, but your shear 10% goes down. If you are going to have your exposed longitudinal prestressing bars, damage state 2, you need to reduce your moment 10%, your shear 25%. And we just didn't come up with those numbers arbitrarily. What we did, we assumed multiple different damage scenarios per damage state or per damage type. We calculated the shear capacity, we calculated the moment capacity of damaged to undamaged one, and we got those ratios. Here is one example. If this girder is the double T that you have, and you are playing around cover deterioration, once take out 25% of the entire cover, 30%, 40%, whatever your damage state will call for, remove concrete, do a moment curvature with and without those damages. The ratio of the peak moments are your capacity reduction factor. We did that not only for one girder, for 25 girders, not only one damage, all of those that you saw in that color table. We did 1,500 analysis, and we came up with this nice summary table for every single double T that has been used in your state. So if you go on a site and you see a damage state of, I don't know, maybe 3 on the exposed longitudinal bar, the top graph will tell you that you need to change your moment, or you need change your shear with those numbers. I think the top one is moment, bottom one is moment 2, flange, stem, and we have the same thing or similar graph for the shear. That's how we were able to tweak the load rating equation and include component level damage into the calculation. I think I'll pause here for any question that you might have.